So thank you all for coming. I'm really pleased and impressed to see so many of you here, especially a lot of longtime friends of Saturday Morning Physics that I recognized for a long time. So I'm going to talk to you today about a research area that is actually relatively new to me, just in the past 9 months or so. I actually grew up as a high-energy particle experimentalist working on experiments at Fermilab for a long time. And then about a dozen years ago, I got interested in the problem of dark energy and why the universe is accelerating. And so I've been involved since then in optical astronomy surveys that are designed to measure the expansion history of the universe and figure out why it's accelerating. And as a byproduct of that, I realized that we have to look through a solar system in order to see outside the galaxy. And stuff wanders into view, and some of it's interesting, and we ought to find it. And so I got involved with searches for new objects in the Kuiper belt in the region beyond Neptune. So that's what I'll talk about today. So before we go beyond Neptune, let's just start with Neptune. Neptune is now the last official planet in the definition of the International Astronomical Union. So that's a lovely picture of this blue giant planet taken by the Voyager probe on its way by. Neptune is not visible to the naked eye. It was the first planet to be discovered by mathematics, by a pure work of intellect. It was realized that the orbit of Uranus was not exactly in line with predictions. And so through just an amazing tour de force of calculation, I can't imagine how one did this before you could do it on computers. On pencil and paper, the perturbations were calculated and were pointed, told where to look, indicated where Neptune was, and it was found near where it was predicted to be. Neptune is in a nearly circular orbit, like most of the major planets. And a unit I'll be using a lot in this talk is the astronomical unit, the AU. It's a sort of standard yardstick in the solar system. It's the mean radius of the Earth's orbit. The mean distance of the Earth from the sun is 1 AU. So Neptune is 30 times more distant from the sun than the Earth is. Neptune is also kind of geometrically in between the Earth and Jupiter in terms of its mass. It's about 17 times more massive than the Earth, about 17, 18 times less massive than Jupiter. So it qualifies as a giant planet, but not too giant, not as giant as Jupiter is. Okay, and then of course, beyond Neptune, there is the first trans-Neptunian object discovered in the 1930s. That's Pluto. They didn't know it then, but what was found was the first example of an object in the Kuiper belt. So here is Pluto on January 13th, 1930, this little dot here, and a few days later it's moved over to here. Clyde Tombaugh did this work by painstakingly, mechanically clicking back and forth between plate after plate, looking for things that moved, and having done this now myself with computers, I know there's lots and lots and lots of things that move, and it must have been just incredibly tedious, mind-numbing, not to say work, but it finally paid off in the discovery of Pluto. I'll have more to say about Pluto a little later in the talk. So many years passed until the next object beyond Neptune was found. It wasn't until the 90s that the first other thing out there was found. 1994 QB1, I think it's called. And in the couple of decades since then, several thousand new objects have been discovered out beyond Neptune, and they roughly fall into 4 different categories. So there are classical Kuiper belt objects that form this kind of donut-shaped ring out at about 40 AU-ish. Remember, Neptune's at 30. The Kuiper belt is believed to be the source of short-period comets, things that get perturbed and end up on a trajectory that takes them into the inner solar system. Threading throughout this population is a set of resonant KBOs that are in a special orbital relationship with Neptune that make an integer number of orbits in the same time period that Neptune makes some other integer number of orbits. For example, 2 orbits for every 3 that Neptune makes, or 1 orbit for every 2 that Neptune makes. There's also a population of what are called scattered disk objects that don't lie inside this fat donut and aren't in a special orbital relationship with Neptune. These have higher inclinations, generally higher eccentricities, not so much in the plane of the solar system, Some of them are quite distant. They include some of the other dwarf planets. And then finally, out beyond there and extending far beyond the reach of our telescopes, all the way to the hypothesized Oort cloud at thousands of AU, we have these detached objects, these inner Oort cloud objects, that never approach the rest of the solar system close enough to have an interaction with the major planets in any significant way. The solar system to these things looks like a distant point mass. So these are very rare. There's only a handful of them known. These are believed to be the source of the long period comets. So it's quite a population of interesting things out there. And here's one way to visualize those. So this is a plot showing the semi-major axis of the orbit, the size of the orbit in astronomical units on a log scale. So I've put a few key spots along the x-axis here. And then on the vertical axis, we've plotted the eccentricity of these orbits, how stretchy they are. So an eccentricity of 0 is circular. An eccentricity of 1 or greater is a not closed orbit. It's open, parabolic or hyperbolic. And then the larger the number between 0 and 1, the more stretched out this orbit is. So here at 30 AU, that's the position of Neptune. Neptune is at 30 AU and at an eccentricity of about 0. Then you see this band of purple objects here, a bunch of objects clustered near 40 AU and at a range of eccentricities. So these are the objects that make 2 orbits for every 3 that Neptune makes. And they're called Plutinos. 3 guesses as to why. So Pluto is one of those. Pluto is about here. And there are a number of other such things. There's another purple band right here at about 47.7 AU. Those are called the Tutinos, in a play on word with Plutinos. So they make 1 orbit for every 2 of Neptune's. And then there's even a faint purple band a little further out that are objects that make 2 orbits for every 5 of Neptune's. All of these special resonant orbits are special because they're stable. They protect the object against ever getting too close to Neptune, because whenever they get near Neptune's orbit, Neptune's not there. Neptune's in one of several places not close by. And I think that's easiest to see for the Tutinos. So if Neptune is here and the other object, when it gets close to Neptune, is over here, then by the time the object gets back to here, the next time around, Neptune's gone around twice and it's still over there. So these objects tend to pile up in these resonances because they're stable. Once they land there, they don't leave. Here's a side view of some of these things. And you notice that, that there's this kind of curve above which most of these objects lie. So that curve is the locus of objects. Any object that lies along that curve will make a closest approach to the sun of 40 AU. So there's many ways that could happen. It could be in a circular orbit at 40 AU, and then it's at 40 AU all the time. Or it can be in a more stretchy orbit and get near 40 AU when it gets close to the sun. And if it's got a very big orbit, it's got to be in a very eccentric orbit in order to get close enough to get 40 AU from the sun. So there is some observational bias in this graph because it's difficult to discover things when they're far away. But it is also believed to be a somewhat accurate depiction of where things are. There seems to be a rather hard cutoff in the solar system of things that don't get closer to the sun than 40 AU. There's very few of them. There's a few, though. You see a few that lie below this curve. And in particular, there's a couple of dwarf planets way out here that never get closer than about 80 AU to the sun. So even at their closest, they're more than twice as far away from the sun as Neptune ever gets. These things out here cannot interact with the planets in their present configuration in any significant way. And so how they got there is a bit of a mystery. Are they objects that had some violent interaction in the inner solar system in the past and they're on their way out? Are they migrating on the way in? Did they get disturbed by some distant perturber long ago and they're on their way in? It's not really clear, and partially it's not really clear because we know of so few of these things. Sedna was found in 2004. 2012 VP113 was actually found in 2013, but retroactively observed, noticed in exposures from 2012. And I'll say a little bit more about that too. So what is going on out at 40 AU? What's it like if you could be there? So this is one of the most famous pictures taken by the Voyager 1 probe, not the Voyager 2 that took that picture of Neptune I showed. This is Voyager 1. As it was leaving the bounds of the solar system, or at least of the planets, at 40 AU in 1990, Carl Sagan persuaded NASA to have it turn around and point its cameras back towards the sun, which the engineers didn't want to do. And it took this picture. And that's the Earth right there. It was the subject of the famous pale blue dot essay by Carl Sagan. A mote of dust suspended in a sunbeam. These rings are just glare from the sun in the lenses of the camera. At 40 AU, the sun shines with 1/1600th of its brightness at Earth. It appears no larger than a dime seen from 100 feet away. And to give you a sense of what that's like, I've got here a little LED. Let's see, that's about as bright as it gets. So if you're sitting in the middle of this lecture hall, then you have a pretty accurate depiction of the apparent size of the sun as seen from 40 AU. Okay, it would be, it's brighter to look at than this, but this is about the right size of it. Okay, so the sun is just a little dot of a bright star. Okay, and probably the brightness of things in this room with the lights out is not too far off from the illumination of the sun of something out there at those distances. So we can turn the lights back on. Thanks, Warren. So this brings me to the Dark Energy Survey and what I and several of my colleagues at Michigan are working on, including Greg Tarley, who gave the Saturday Morning Physics talk last week. So this is Cerro Tololo Inter-American Observatory. It's an excellent astronomical site in the Chilean Andes at about 7,000 feet. There's a 4-meter telescope inside this dome. The telescope itself was built in the early 1970s, but what we and our collaborators did was build a new wide field of view camera, 3 square degree field of view called DE-CAM. The purpose of this instrument and this project is to take pictures of about 1/8 of the sky, 5,000 square degrees, in 5 different colors, optical and near-infrared. It takes a while to do that, so we've been awarded 525 nights worth of time on this telescope, 105 nights per year over 5 years between the months of August and February, so we're currently in the middle of our 2nd season. The goal of this project is to measure the expansion history of the universe, make a sort of time-lapse movie of the last 6 billion years of cosmic expansion and evolution in order to address the most interesting question, the most puzzling question in cosmology today. Why is the universe accelerating? Nobody really knows. And by collecting the kind of precision data that we'll get with this thing, we hope to be able to sort out competing models. And this is a whole another interesting talk, and I think there have been several Saturday Morning Physics talks on this topic. That's not where I'm going to go today, but I just want to mention that it's the main reason that the survey is here. But when you take pictures of 5,000 square degrees of the sky, there's an awful lot of other science you can do besides figure out why the universe is accelerating. Much of it is extragalactic astronomy and astrophysics. There's some things we can learn about the Milky Way and its evolution, different populations of objects in the Milky Way, but we can even learn about the solar system. This is our collaboration. It's a group of institutions in the United States. What? As well as Spain, the UK, Brazil, Switzerland, and Germany. About 125 senior scientists, plus graduate students and postdocs, including a good-sized group of us here at Michigan. So let me talk about the camera, the business end of this telescope. So this is a view of the Blanco telescope inside its dome as they open the dome for the evening to let the temperature equilibrate. And there's a 4-meter mirror down here, and the camera is this black barrel up here. This is what we built. Here's a better view of it from the side. This is the dark energy camera. It's about the size of a kind of a large telephone booth up there at the prime focus. And I know that many of you in here are amateur astronomers. How many lowbrow astronomers are in the house today? All right. Hello, lowbrow astronomers. So this is just a big scaled up version of a telescope that many of us who do amateur astronomy would recognize from our own inventory. So there's a parabolic reflecting meter here in the back, reflecting mirror here in the back, and when parallel beams of light come in from a distant object, they get focused to a point. In a typical amateur instrument, then there's a diagonal mirror that shunts the light off to the side, and an image forms at the eyepiece, and you look at it. In a modern professional telescope, it's more customary to put the instruments right up there in the middle of the top end of the telescope at what's called the prime focus. So we just block out part of the 4 meters of area. There we go. That looks really nice. Okay, so you can see those incoming rays on the top converging and then being bounced off to the side and forming an image up there, there in the eyepiece. Okay. Thanks, Warren. Okay, we'll turn that off. I can turn the lights back on. So this construction of this camera was the main focus of our collaboration starting in 2004. Here is the main corrector lens of the thing after it was cast at Corning in upstate New York back in 2008. The same Corning that makes kitchenware and baking ware. They've got a side business in astronomical glass. It's one Steve Kent wide, and then it takes a long time to figure these things to astronomical precision. So it was the polishing and final figuring was actually done in France. There it is after it was complete in 2011, shortly before it was shipped to Chile to be installed on the telescope. So the optics, the purpose of these optics is to create a flat field of view over this 3 square degree area so that it can be imaged by a set of 62 charge-coupled devices, CCDs, much like you might have in a digital camera. The difference is that our digital camera is about the size of a manhole cover, and it has 570 megapixels. And it operates at cryogenic temperature, so it's very low noise and lots of other special things. So this is an image from the focal plane of the imager here. In fact, this was from the first night of operations. This is one of our kind of famous images. Each image, why do we want a wide field of view? We're trying to map a big part of the sky, and it's sufficiently wide and sufficiently deep and sensitive that every single image we take contains something like 200,000 galaxies. There's more galaxies than stars where we're looking at about 200,000 galaxies, about 100 clusters of galaxies. It's an incredibly rich data set for all kinds of science, not just dark energy. Observing has changed. This is Edwin Hubble at the controls of, I believe, the 100-inch telescope at Mount Wilson in the 1920s, sitting there at the eyepiece and focusing it and writing stuff down and making measurements by eye. This is observing now down in Chile. This is me and one of my shift partners sometime last year. And we don't have enough screens in the control room, so we all bring our laptops so we can get some work done. Sitting there in comfort instead of astronomers used to actually ride up in the cage of the prime focus and be up there bundled up all night. Terrible way to observe because you're generating body heat and messing up the air. It really affects things. So we're much more careful about those things now. So it takes beautiful pictures. This is a close-up of that galaxy that you may have noticed in the bottom of that focal plane mosaic I showed you. This was actually taken on the first night of operation back in September of 2012. We pointed it at bright, beautiful objects, and it just worked spectacularly well. Here's another picture. DES. And this picture is a sort of kind of a personality test. So to see if are you a cosmologist or not, you can take this test too. So what's this a picture of? Is this a picture of a beautiful spiral galaxy? Or is it a picture of a large, annoying foreground object that's covering up all the interesting stuff behind it that you can't see? Okay, if you answer B, you may be a cosmologist. All of these interesting high redshift galaxies, these little red dots, where the real action is in cosmology, and then there's this stupid thing in the way. Okay, so it's not all fun and games up there with dark energy and comfortable control rooms. Once in a while, we're called upon to save the planet. So last February, we got this urgent request to the director of the observatory saying, can you please take 10 or 15 minutes out of your important dark energy business to observe a critical near-Earth object on a potentially hazardous orbit. It's getting closer to the sun, and it's going to be lost, and it's cloudy in Hawaii, and help! 5 30-second exposures centered on blah, blah, blah. Okay, so our intrepid crew did this, and so there it is. There it goes over. These things are moving. There it goes. It's turns out to be about 130-meter sized rock located about, in this particular case, about 40 million miles away. So it shows you the power of this instrument to see, little things at big distances. So thanks to these observations, we were able to determine that it was not going to hit the Earth. It was going to miss us by millions of miles, posing no threat to the operations of our experiment. Okay. But this got me thinking about what else we could do with DE-CAM in the way of solar system objects. And near-Earth objects like this are actually very hard to do in a systematic way with DE-CAM. They move very fast. We can't interrupt the exposure scheduler of the survey to kind of follow stuff. And so there's not much we can do, although we are occasionally asked to do targeted follow-up by the large community that does track these things. But trans-Neptunian objects are a nice thing for us to go look at. And so here's a picture that shows the current positions of about 1,000 known objects in the Kuiper belt and beyond. So here's that fat disk that I was talking about, and this is the ecliptic plane that sort of threads through the survey, not quite aligned with the plane of the Earth's rotation. This blue tank-shaped area is the survey area that Dark Energy Survey will map out. So you see that there's a lot of stuff that passes through. That's where those things all were at the start of our observing program 2 years ago. I want to point out that 1,000 sounds like a lot, and it kind of is. On the other hand, there's nearly 1 million main belt asteroids known, and dozens more being found almost every day. So main belt asteroids are in some sense a dime a dozen, but these KBOs are still kind of special and rare. So here's where these things were, and you might want to know how do they move over the course of an observing season, and that's what they do. So there's a few high inclination ones that kind of move rather fast and duck in and out, but most of them undergo this back and forth kind of sloshing motion. Mesmerizing. I could watch this for a long time. Okay, so why is that? So it's not that they're actually moving back and forth. What's going on is, of course, is that the Earth is going around the sun, and so we're seeing these things from a moving platform. And as the Earth moves from one side of the sun to the other, and then to the other and back again over the course of a season, these things move comparatively little, and what we're seeing is the parallax of these things against moving back and forth against the fixed background of the stars. Okay? And one point I want you to take from that is that they move relatively slowly, and so it makes sense that a program that is on the sky for 5 years could track these things in a systematic way. The power of our camera to make important new discoveries in the solar system was illustrated in the very first month that the camera came into operation. You remember 2012 VP113, that little dot out there at large perihelion? It was discovered with DE-CAM, and it turned into the very first paper in Nature, the very prestigious science journal, from this camera. Unfortunately, it wasn't from us, but these guys, Trujillo and Shepard, discovered this object, 2012 VP-113, that has the largest known distance of closest approach to the sun of any object in the solar system. It never gets closer than 80 AU. So it's a remarkably distant object. It was a tour de force on their part to discover it. It was discovered so that we don't have use of this camera the whole time. There's other nights that are available to the astronomical community, including the whole time between February and August. They got a couple of nights in November and December and carried out a program that found this thing. So this was very exciting. This was New York Times and NPR, and it was big news because things like these are extremely rare. Really only the second known example of an object that's that distant. So it gives us some hope that in a more systematic survey, this is the kind of thing that we can find more of. So I was casting about for, this was around last spring, I was casting about for projects that would be good for summer students to work on. People talk about the incompatibility between teaching and research, but honestly, this originated for me as a project intended for students. I don't think I would have gotten involved with it had I not had it in mind as a student project. And so I took on a couple of summer students who happened to be from my undergraduate alma mater, a couple of really gifted students. Have a couple of students now working with me from Michigan. These guys really participated intellectually in this in an important way, made really crucial contributions to the project. So there they are. So where did we want to start looking? So 5,000 square degrees is a big area to look in. And we don't image any one part of the sky very often, which makes it hard to find things that move. Except we visit these 10 specific areas on the sky, these little blue, dark blue patches, about once a week for the whole course of the season. Of course, we're not doing it to search for TNOs. We're doing it to search for type 1a supernovae, which if you're an aficionado of Saturday morning physics, you probably know that type 1a supernovae are standard candles that are used to measure the expansion rate of the universe by measuring the distance redshift relationship like Hubble did. So these are, again, that's a whole separate talk. But the supernova people in the Dark Energy Survey are interested in looking at these same areas of the sky over and over again so they can look for new things that appear and get bright and then slowly fade out over the course of a few months. For a while, they're as bright as their whole galaxy. And over the course of our survey, we will expect to discover about 3,000 of these things and make this distance redshift map. So it's a primary science goal of the survey. But you notice that 5 of these fields up here, the so-called S and X fields, are they're relatively close to the ecliptic. We might expect to see KBOs wandering through. These other fields are further away, but anything we find down there would be weird and interesting, so they're a good place to look to. And these things, as you saw, move slowly enough that they can actually stay in the field for weeks and months at a time. So we can track them and not just kind of see them on one night and then they're gone like the near-Earth objects. So the supernova community has refined difference imaging to a high art form. Remember, they're looking for new things that appear in one place and get brighter and then fade out. So in order to do that, this used to be done in the old days by visually scanning images, and I think people's significant others that destroyed too many relationships, and so now we have computers do it. So you basically are looking for things that change. And so you have a reference image. You take a new image. You subtract the reference image from the new image. And what's left, in principle, is stuff that changed. Turns out lots of stuff can change. Some of it's supernovae even. But in addition, we have moving transient objects, a lot of main belt asteroids, a few KBOs. Mostly, though, what difference imaging finds is junk. Lots of artifacts, and this is the most prevalent thing by far, probably by factors of 100 or 1,000. It's just very, very difficult to subtract images and not have residue left over. And they've gotten very clever at throwing out a lot of the junk. So what we're left with is a list of relatively high-quality transient things. So our strategy to search for these things was to look for good detections from the difference imaging. And then it takes 3 points to fit an orbit. You can't just look at a thing appearing on 1 or 2 occasions and say, that's a TNO. You need 3 sets of observations to fit an orbit. And so we tried to identify triplets of points that came from different nights that were separated in a way that looked like they were moving like a KBO. And then we'd fit it and then see if it was consistent, and if it was, try to add more points. I'll just say a little bit about seasonally appropriate motion. So most of the solar system objects we observe at that time of year are moving backwards on the sky with respect to the fixed stars. What just happened? Okay. That's because we're moving faster than the things to the outside of us in the solar system are. So as we pass something on the inside track, it was here, and then it was here, and then it was here as we projected onto the background of the stars. So when the object is opposite the sun in the sky, it will undergo this so-called retrograde motion. The more distant it is, the larger the fraction of its time it spends in retrograde motion. And so if you could imagine suspending out there in space at 40 AU, a stationary object, then its apparent motion on the sky would be this sloshing motion that we saw in the real KBOs. Now, real KBOs are moving so that they're superimposed on this pattern, a very slow drift. But to first approximation, they're just tracing out these ellipses depending on what time of year, October, November, these turning points in February and August, and then in this part of the year when we're not on the sky, it's moving in the so-called prograde direction. Okay, so we're looking for things that are kind of making these swooping swoosh motions like this. So that's how we group our triplets. I'll just say briefly how we describe an orbit. I talked about the size of it, the semi-major axis, the inclination, how tilted it is, the eccentricity, how stretched out or circular it is. There's a couple of other parameters that describe the orientation of the orbit in space. And then there's a final parameter that tells you actually where the thing is in its orbit. Where is the object right now along this shape? Okay, so that's what we are fitting when we fit an orbit. Now there's 6 parameters, and so that's a little hard to visualize. And so, in order to make sense of our data, what we decided to do was to make a plot of just 2 of those parameters, the semi-major axis on one scale and the inclination on another scale. So it turns out semi-major axis is not as well measured with 3 points as inclination is. So we made some fake data. We put in a fake KBO. We tried fitting the triplets we found that met our criteria. And you see a lot of random points from random combinations. But the real KBO, triplets from real KBOs should fit the same orbit. And so they tend to have the same inclination and more or less the same semi-major axis. Okay, so that's the idea. And so we were excited to try it with the real data. Now, the real data is, there's a lot of real data. So this is one of those focal plane mosaics from DE-CAM. And to give you a sense of the size of our focal plane, that's the size of our field of view on the sky relative to the full moon. Okay, so the full moon is about ½ a degree. Here's our 3 square degree field of view. Okay, so let's not point the thing at the moon. So here's a typical raw image from one exposure on one night. Remember, about 200,000 detected objects in this exposure. Let's zoom in on one of these CCDs, one of the 2K by 4K CCDs, that one, and let's blow that up. Okay, there it is. And you see a little more detail. There's lots of stars and galaxies here. Let's zoom in a little bit more. Let's zoom in on that region up there, okay, near the bright star. Can you spot the KBO yet? Okay, it's not the bright star. By the way, that star that looks blindingly bright is not visible to the naked eye. But it's blindingly bright to a 4-meter telescope. For the astronomers, it's a 7th magnitude star. So let's zoom in right very near the star to this area right there. And so where's the KBO? It's that thing. Okay. How do we know this? Okay. Well, so this is where difference imaging comes into play. So there's that thing. What difference imaging does is overlays this exposure with an image from another night. So here's an image from another night. See? Whoops. Oh, no. Now I got to do this whole thing again. Okay. Okay. Zoom in, zoom in. Sorry about this. But I did spend a lot of time on this slide, so I might as well show it to you twice. Okay. So overlay a different night. Then we set them side by side. And then we do this difference imaging. So here's the search image. There's the reference image. There's the one subtracted from the other, and there's something left over. Okay, and it's that. Okay. So what we get from the supernova people who are trying to measure the expansion of the universe is we get a whole list of things like this. There was a dot here on this date at this time. And of course, that doesn't make it a KBO or anything else. It may be a supernova. The way that you decide what it is you look in different places on different nights, and you see it moving like a KBO is supposed to move. So we moved on to the real data. So this is what we saw when we looked at the first supernova field, which was a little disappointing. There wasn't any of those little lines like we expect to see if there's a real KBO. But my intrepid students were undeterred by this, and we moved on to the next supernova field, and we saw stuff. Okay, we saw stuff. We found some real KBOs, and so this was really exciting. One of them was that thing that I just showed you on the previous slide. And now that we've flipped left to right, so up here in the upper right-hand corner is that first point there in the corner of the chip near the bright star. And then over the succeeding couple of months, we saw it moving across the focal plane systematically on different visits to the same field on different dates, and could fit it to an orbit. And so this is henceforth known as 2013 QO95 with a semi-major axis of about 40 AU, right out there in the Kuiper belt, a fairly circular orbit, but inclined at 20 degrees to the plane of the solar system. So there it is. So we were excited. Now I'm often asked, what do these things actually look like? They look like this, at least to us. We think, though, that if we could get a lot closer to them, let's say we could hover, a few kilometers over the surface, they would probably look a lot like this. Okay? And so I'm sure that you all have been following the really fascinating story of the Rosetta probe and its lander Philae. Just this incredible technical tour de force of getting to this comet over the course of 10 years and getting into orbit around it and dropping a lander onto the surface, which unfortunately seems to have bounced into a shady spot and its batteries have run out. But it's, hopefully they'll find some clever thing to do, or maybe as the comet gets closer to the sun, it will get a little more sun and wake up again. But just nonetheless, I think that doesn't diminish the incredible technical accomplishment and sort of human triumph of being able to pull this off. So we think that comets are made of the same stuff as these objects out here. And so even though we can't discern any structure of these things at all from the Earth or even from the Hubble Space Telescope, one believes that they come from a population very similar to these comets. So you saw on that picture that these things are quite faint, that the glare of this star that you can't see nearly washes this thing out. Can you go find them in your backyard telescope? Unfortunately not. They are about as bright. So this is the most dangerous demo they let me do now. Okay. So here's a candle. And the people in the next room will just have to imagine a candle. And now imagine taking this candle about 40,000 kilometers away. And this is what we're looking for with our 4-meter telescope and our camera. That's about how bright these things, these Kuiper belt objects, are as seen from Earth. This is why it took another 60 years to find the next one after Pluto was found. Pluto turns out to be an extremely unusual Kuiper belt object in that it's rather large, 1,200 kilometers, and it is extremely reflective. It reflects about 70% of the incident light on it, and so it's anomalously bright for a Kuiper belt object. Okay, thanks, Warren. We can turn the lights back on. Most of these things are both smaller and darker than Pluto. Okay. So I'll just say a little bit about a few of the other interesting things we found. Here's another object, 2012 VR 113. So we originally found it in the same data from a year ago that we found that other one in. But we were on the sky a little bit in 2012. Remember those pictures from the fall of 2012, including the discovery of the other distant object. And so we had a good enough orbit that we could predict its position a year ago to a gnat's eyelash. And so we looked, and there it was from the year before. This turns out to be one of those resonant objects I mentioned at the beginning of the talk. This makes exactly one orbit of the sun for every two that Neptune makes. And it, therefore, never has a close encounter with Neptune. This one is, we don't know the size. We know how bright they are, and if we make some crude estimates of how much light they reflect, this thing is probably about 280 kilometers. Could be smaller if it's more reflective, but approximately, a little under 300 kilometers, perhaps. An object is thought to have to be about 300 to 400 kilometers in size to become round, like a planet, for its gravity to form it into something round. So we don't know what shape this is. It might look like that knob of ginger, like the comet looks like, or it might be a little round. We just don't know. And we'll probably never know until some space probe gets out there. Okay, so there's a comparison image on the discovery night and some other night when it's moved on. This one I think is my favorite, 2013 TV 158. There's two images taken 2 hours apart just this past summer. This turns out to be one of those very distant scattered disk objects, way out that curve. So it is in an orbit that is nearly 1,200 years long. So the last time it was here was around the year 800 AD. People couldn't see it back then. It's highly inclined at 31 degrees. It's quite eccentric. And this one's actually pretty bright. It's a little bit bigger. This may be dwarf-ish, planet-ish. And it will reach perihelion, its closest approach to the sun, in just a few years, comparatively speaking, on August 22nd, 2022, plus or minus a week. It's not an accident that we're happening to find this thing near its closest approach to the sun. That's when it's closest and when it's brightest. The apparent brightness of these things falls off like the inverse fourth power of the distance from the sun. It's an exercise to the reader to figure out why, but that means that if it gets twice as far away, it's 1/16th as bright. If it gets 3 times as far away, it's 1/81st as bright. So we're highly biased against finding things when they're close. In fact, we estimate that this thing would be undetectable, even by our camera, over 90% of its orbit. Of course, there's probably lots of other things like this out there that are in the other 90% of their orbit, and we'll never see it, but someone in the future will find them. Okay, so this is that object, and you can see that its orbit is quite a bit larger than Pluto's, and Jupiter is a inner solar system object in comparison. Here's another one that I like. This was found just a couple weeks ago by me and the new undergraduates. So, and the most recent point came from just earlier this week. So we're tracking this one right now, and this one's a Plutino. So it has an orbit that is nearly a copy of Pluto's. I've put here its orbital parameters and Pluto's in comparison. The orbit is shifted relative to Pluto's, but otherwise it's the same orbit. It's really the same thing. It's just a lot smaller. This is quite faint. This was probably just 120 kilometers in size. The background image here is the image from this past Wednesday morning. And where is the thing? It's that. Okay. Our computers are really good. So this is why. How many of you were upset when Pluto got demoted? I know, right? I was upset. But the more one learns about this population, you realize that, there's that whole big lot of Plutinos out there, a lot of things that make 3 orbits, that make 2 orbits for every 3 that Neptune makes. So Pluto is the largest. Pluto is an exemplar of a class. It's not a thing that stands on its own. Nonetheless, this didn't stop third graders from sending hate mail. It didn't prevent civil unrest from breaking out, other forms of peaceful protest. Walt Disney would buy Pluto. I like this one. So, Pluto means a lot to people. I kind of like Pluto. But I think instead of lamenting the demise of Pluto as a planet, it's more interesting to think about this whole new category of objects, these dwarf planets, and how they got there and what they might tell us and how many more there may be. So the last one I'll mention, and this was discovered a week ago yesterday, is 2014 QO441, as it's been dubbed by the Minor Planet Center after we sent it in. This is a special object because it's a Neptune Trojan. Now, Trojan asteroids are a special category of things that are in the 1-to-1 resonance. So they're in the same orbit as their major body, but a little ahead or behind. It turns out that there's a couple of stable points that lead or lag the object by 60 degrees, by a 60-degree angle here with respect to the sun. Jupiter has a whole armada of Trojans at both of these so-called Lagrange points. So these are in stable orbits. They're roughly at the spot where the gravitational pull of Jupiter, or in this case Neptune, and the sun is the same. And it turns out to be a point of stable equilibrium. Here's all the main belt asteroids in white. You also see that Jupiter has another family of resonant objects. They're those little red dots, the Hildas, that are in the 2-to-3 resonance. The difference is that with the Plutinos is that these ones make 3 orbits for every 2 of Jupiter. They're inside Jupiter. The Plutinos make 2 for every 3 of Neptune. They're outside. But it's the same kind of thing. So they're at these angles apart, and they never get close to Jupiter, and they can kind of stay put. So this is a Neptune Trojan. So it's leading Neptune by 60 degrees in its orbit. And here's this thing in a 1-hour exposure sequence taken in early September. So let's roll this. Okay, so you can see it moving. There it goes. The seeing improved over the course of this hour, and it kind of crispens up there near the end, but you can still make it out. It's moving very slowly. Mostly the Earth is moving. That's mostly the motion of the Earth. Okay. Neptune is thought to have many Trojans, but this made number 10. There were only 9 previously known. So this is a pretty unusual object. Is it really stable? Well, fortunately, we have one of the world's foremost experts on planetary system dynamics here in the faculty of Michigan. In fact, he introduced me. It's our own Fred Adams. So Fred has analyzed the orbit of this object for a period of for thousands of orbits, about 1 million years, and finds that it's in fact stable, at least on that time scale, for several thousand orbits. Now, it doesn't just stay there at that Lagrange point. It's actually in a stable motion around that Lagrange point. So if you could sit on Neptune and watch the path that this thing made in the sky, it would look like this. It would be kind of executing these swoopy patterns around the Lagrange point, and at the same time corkscrewing back and forth along the orbit, backwards and forwards with a period of what, a few thousand years, Fred, for a complete back and forth oscillation. These here are the annual motion. One of these loops is what it does in the course of one orbit around the sun every 165 years. So this is really cool, and again, it's quite new. So to sum up what we've been able to accomplish in the past 2.5 years of looking for these things, I made a little movie. So this is the situation in 2012 in November, right before we started observations with our camera. And these are 3 of those supernova fields, the X fields, with our focal plane kind of illustrated on the sky where they're pointing. Okay? And so it's November 2012, and we know nothing. And what will happen here is that as I roll this forward in time until February of 2015, the end of the current season, objects will appear here when they're first observed, and the red dots are at sometime when we saw them. Okay, so we'll roll this. So here's a few objects that appeared early in November. This one looped through that field in the very first season. Now it's the summer, so we're not on the sky. And now it's August of 2013, and the new season starts, and we start to see the new things that have wandered into the field and track them over the course of a season. Now we're off the sky again. This is the summer of 2014, spring and summer. The Earth is coming back around the sun. Now it's August. And now the current year starts. And we start to see a few more things. And finally, the current year will end in February. So these things, here's that elliptical motion, but superimposed on it, the slow drift of these things across the sky as they undergo their own particular orbital motions. You see that we've recovered a few of these objects outside the supernova fields in the images we're taking the rest of the time in the full 5,000 square degrees. So all told, we've found 11 of these things so far. Here's some of the particulars if you're interested. Another, we think we have a 2 to 5 resonance. We have the Plutino, a Neptune Trojan, this object with a period of 1,200 years. So to put these objects on the scale of where the rest of the KBOs are, our observations are the red stars. So here's our Neptune Trojan there at Neptune. Here's our Plutino. A couple of others are Plutino-like, but probably not quite there. Several 2 to 1 resonant objects. There's the possible 2 to 5. And here's TV-158 way out in the boondocks. So we expect to find many more such things. But of course, where we'd really like to be is out here in the world of VP112 and Sedna. And fortunately, we have, so what are these things? They can't interact, and how did they get there? Fortunately, we have 5,000 other square degrees to play with, and we've only looked at 15 square degrees so far. So this is a somewhat more technical plot, but basically what this is showing is survey coverage and area on the y-axis, and how faint can we go on the x-axis. So going faint is good, and covering a large area is good. So the most sensitive surveys are up in this corner, and this is where we will be compared to other ongoing surveys. So we estimate we can discover factors of tens, at least, more of these things than prior surveys. But it's a challenge because we only image each of those points in the wide survey a few times a year. And so instead of linking to the next point the next week, we might have to link to the next point 8 months from now when it's gone around and gone around. And so these plots are going to look a lot more like this with just a few dots on them. And it might take several years to get enough data to really do it. We don't do difference imaging in the wide survey yet. We need to develop it. And if the fake rate is not low, our computers are going to have an awful lot of work to do. So we have a lot of work to do to keep the fake rate down from the difference imaging. I think I'll skip this. This says that we're sensitive to the objects at high inclination that other surveys would miss, but those are the interesting ones. So to conclude, this trans-Neptunian solar system is a poorly explored place, but because it's this preserved fossil record of the early solar system, and it consists of the objects that got left over when the rest of the solar system was formed, it's a unique record of what formed the solar system, what continues to shape newly forming solar systems, extraplanetary systems, and so it's very worthy of study. We've observed 11 of these so far in the supernova fields. We didn't find anything that was already known. All 11 things that we actually found were new. It's not like there's 30 more that I didn't tell you about because they were already known. Everything we found was new. So it tells you the power of this instrument that where we point it, we will find interesting new things. So less than 1% of the full survey area, but we've already found, 11 is 1% of 1,000. And so we found about 1% of all known TNOs and now 10% of all Neptune Trojans. But we've got 5,000 square degrees more to look in. And so by the end of the survey, we anticipate finding hundreds more of these things. And it's difficult to extrapolate from 2, but perhaps a dozen of these weird things way out there, we don't know. In any case, by doing this, we hope to do a full census of the outer solar system and much better characterize these different populations that tell us about our own origins as a solar system. So finally, I want to thank my collaborators at Michigan and in the broader collaboration, my students, the funding agencies who make this all possible, and of course you, the taxpayer, and in particular, friends and supporters of Saturday Morning Physics. To learn more, you can find our website, follow our blog, follow us on Facebook, and the Minor Planet Center has all the information you could want about minor planets. So thank you all very much.